In this class, I'm not going to ask you to calculate moments of inertia very often from first principles. I'll either give you the moment of inertia of an object that's complex, or I'll tell you that it's a shape that comes from one of the standard lists, and I'll ask you to know certain formulae for the moments of inertia of different shapes of objects. So please know these particular shapes. The first is a point mass. If this point mass is moving at a distance r away from some center of rotation, in other words, it's making a circular path around a center of rotation, its moment of inertia is just mr squared. So whatever r is the distance away from its circular path, you should know that mr squared is its moment of inertia. The next is a hoop. A hoop consists of lots of little point masses, all a distance r away from its axis of rotation. So if this thing was spinning like a frisbee around the dotted line shown in red there, the moment of inertia of this thing is also mr squared. In other words, it's got a lot of smaller masses added up together makes the mass m, but they're all at r squared. So that's going to just be mr squared as well. The next is a disk, and you can imagine throwing a pie plate through the air so it acts like a solid frisbee. This is got a different moment of inertia because some of its mass is concentrated at smaller distances than r. The moment of inertia of a disk is 1/2 mr squared. The next is a sphere, and if you imagine a planet rotating and spinning around its axis, the moment of inertia of this is 2/5 mr squared, lots and lots of mass at different radii, and so it's even smaller than the disk. The next is a rod. If we imagine spinning it like a baton around its center, so it makes like a propeller shape, the moment of inertia of this is 1/12 ml squared, where L is the overall length of the rod and m is its overall mass. And the last is a rod that's being spun around along its long axis, so it's like a drill. If this thing has a radius r, then its moment of inertia is going to be 1/2 mr squared. Notice it's the same formula as it is for the disk, because viewed from the end, this rod is nothing more than the disk. Now its mass might be overall bigger because it's a big long rod, but its shape isn't really, the length of its shape isn't really affecting its moment of inertia, because we're just trying to calculate how much mass is away from the axis of rotation. So for the disk and the rod, it actually turns out to be the same. Again, what I'd really like you to do is to know the formulae for these shapes. On equation sheets for exams and so on, I'll try to give them to you, but rest assured these are some numbers, or these are some formulae that you should just kind of get familiar with.